Thank you very much. So my name is Vera Könyves. I'm a researcher from the Hadan-Saki, the Institute for Computer Science and Control. And the background for the title is that originally I'm an astronomer, astrophysicist, and I was working until recently as such, mostly abroad for 15 years. And today I'll a little bit of this and that to you. So I'll talk a little bit about astrophysics, then energetics, and then robotics as well. Let's start with some astrophysics with no AI for the moment. So in a Herschel, we don't need that. So in a Herschel Space Observatory project, I was working for a decade in France. We observed several interstellar molecular clouds in our galactic neighborhood. For example, this beautiful image called W40 is basically the densest dust and gas parts of a molecular cloud, which can be seen in the direction of the snake serpent's constellation. It's at the distance of about 1,400 light years, which is on galactic scales. This is really the neighborhood. And each color in this image basically is a wavelength or the combination of the wavelength in the 70 to 500 micrometer wavelength range, which are exactly the wavelength ranges where we can see the diffuse and even the more compact interstellar matter, knowing that stars are forming in the densest and coldest regions of the molecular cloud. So first, mostly due to gravity, the matter will be pulled and compacted into elongated so-called filamentary features. These we can see here and here, these elongated stuff, which are the densest and the coldest parts of the molecular cloud. And within these, the clumps, or later on, the so-called more denser prestellar cores, these are the seeds of the future star generations, in which then nuclear fusion can start at some point after accreting enough material, so collecting enough material from the direct surroundings. And basically, in a nutshell, this is how solar type stars form together with the dusty accretion disks, from which then planets might form as well. In having in hand all the specialized tools for each and every step of these data analysis, we do not necessarily use AI or machine learning models yet, just yet in these works. However, my plan is that what I showed you in here, a couple of references. I'd like to use, I want to figure out how I could use AI and machine learning, most probably with students on my data and papers. And here, this piece of sky is exactly the same as the one before, but at a much shorter wavelength, infrared wavelength, where you see that there's less cloud material, but many, many more stars, and both in the cloud and in the background. So now let's jump to another astro project where we do apply AI with students. The original idea is coming from Professor Pista Csabai, who was here yesterday in the morning. So the data we're using from the SDSS Sky server, the SDSS is an international collaboration, which is gathering data from 2 American telescopes, a north and a south one. They are collecting photometric and spectroscopic data for many, many stars and galaxies. This is about the structure, to reveal the structure of the near and the far universe, basically, this project. And so we can visualize these many, many galaxies like this in this zoom-in image where all these light blobs are faraway galaxies. And so what's the Sky server? The Sky server is a huge platform where both the data and the computing power can be available. And let's keep it simple. among other things, in this database, basically we have tables and functions. And a function, for example, is which calculates the distance between two sky coordinates. Think about these kind of things. And naming these tables and functions in this small SQL code, this simple way, basically, we can find galaxies within one arc minute of a given sky coordinate. And we would do this operation to then later on further analyze the subset of the galaxies for our own research. But why do we want to create such a text-to-SQL framework when researchers can do programming? Well, so physicists and astronomers, certainly, but not everybody. For example, high school students might want to access the database with a motivated teacher for a small science project, whether in Hungary or not. I don't know, but let's make then these pool data more available. On the top of that, if we set this up with the SDS Sky server, we might use that on some other also well-established databases, whether astronomical or not. And so that's why we are doing this job. That's why it makes sense. And what we use to then get the code from text is Vana AI, this framework. This is an open source Python RAG framework. And I won't really talk much in detail about LLMs, large language models, but I don't know if RAGs, retrieval augmented generation, if does it ring a bell? But maybe 2 sentences on that. So these RAGs, retrieval augmented generation, which is in the heart of our framework. So this is basically just a technique which can improve the quality and the accuracy of the generated text to have it more fact-based and without hallucinations. And it has 2 layers, 2 components, a retriever. First, it will go to an external knowledge base for relevant information. That's our database. And then the generator, that's like a language model. And then this language model will use both the input query and also this retrieved information and document to then generate a more accurate answer, basically. How does it work? You type a query first, an astro query, list the elliptical galaxies around the sky coordinates, I don't know, the faint ones given by some parameters, for example. But we still need to transform this text into numerical vectors because the LLMs understand only mathematics. So that's why we have there the vectorizer bots. And then the LLM will spit out the SQL code that we run on the database and figure out whether the answer was correct or not. This is how it works. Basically, we already have a paper in preparation. We are still changing the modules, as you can see in this representation. So this one framework is modular. So you pick the database, the vectorizer, the LLMs, and even the front end. And so we are still changing, for example, the LLMs. Mostly we're using the ones which are available on the Hidden Cloud Gen AI for Science service. And we train on the question, code, answer triplets. We also have more metrics, a hard one and a soft one to evaluate our result. And now, change of topic. Let's now go to whatever I'm doing in here, whatever I'm showing, it's under the hood of the AI laboratory of Stucky or the AI National Laboratory. I'll comment on that later. So a little bit of energetics because we can improve power network forecasting as well with machine learning methods. So last year we had a project, a very pleasant and very effective one, 5-month-long project with Mavir, which is the Hungarian transmission system operator, and also with the Technical University's Faster Research Group. So among other things, with my colleague in the AI National Laboratory, our task was to forecast the electricity network loss. And basically, Mavir is doing this forecasting job with their own methods for decades, and pretty well, actually. But they very wisely, they wanted to see such results with AI, and that's why they gave us a lot of data and very good quality data. And this is key for forecasting, forecasting, as we know that very well. However, these data are pretty confidential, so I'll show you what we did to another project. So instead, let us then predict the total load. Let's forecast the Hungarian total load. And the total load is basically all the generated energy per country. This is not exactly the consumption, but ideally it is. So we're downloading data from the ENSOE platform, which is keep publishing in every 15 minutes, actually, all the network loads and also the energy transmission between the countries, and also the officially given per country forecasts and predictions are also available in this on this platform. And here in this graph, you can see 1 day of the Hungarian total load, which has a structure, no surprise. So not much during the night in here. Then the morning peak before going to school, and then an evening peak as well. That's around 7, 8 o'clock in the evening. But before we then load our data, these base data in our machine learning models, we need to understand them, check them, clean them. And we also generate statistics out of all these data. We transform them a little bit. And it is also a very good idea to include some other properties and features which might also be related to the power network, such as date information or weather meteorological information. And after cleaning all the messy data, rearranging them, the nice features we can then load in our machine learning model. And after trying out more, we are using for these purposes XGBoost, which is a decision tree based gradient boosting method. It has a lot of advantages. You can use more than 1,000 features, but though we didn't use these many, it can learn from nonlinear data patterns. And also, if the within this XGBoost, the weak learner trees that you can see in these gray boxes are not deeper than 3 layers, as it is here. We, even the human, can understand the learned decision logic, and this is a very good thing if this is, for example, a business project and the partner wants to know much more about the results, to see beyond the results. Or interpretation, these 3 layers, we can understand 10 layers, not really. So this model was trained on 3 years of total load data. And here in this graph, I can show you a part of the evaluation period where we can see on general that our green model is much closer to the official total load, the actual total load, than the red officially given predictions, which is a good thing to us. And it's also very important beyond the results to give interpretation of the results. And well, if we can, depending on the model. And with XGBoost, we can, because this is a very well interpretable model. And there are mathematical tools for this. For example, the SHAP method, the shapely additive explanations, which is based on game theoretic approach to calculate the contribution of each feature we are using to the to calculate the contribution of each feature to the final predicted value. And then we have done all these and figure out that basically the time, date related features, whether it's a weekday or a weekend day, and also weather meteorological related features, whether it's sunny or not, these matter much, much more than some other features in these load exercise. So what I was going to say, other things, I think that's it on this. This is now just a little place for advertising. So Sam, our colleague, he submitted his MSc thesis last week, in which he was using graph neural networks to predict the electricity price in many European countries, basically. And you can see that too, that basically the power network, you can consider it as a graph throughout Europe. And by now we are able, as it was not quite the case like 8 years ago, we are able to more conveniently use, let's say, for example, graph convolutional networks and leverage the graph structure and property of the data. You do not need to save out timelines out of this because the model is digesting the data directly in graph structure. So so this is somewhat more sophisticated than the XGBoost. But of course, you choose your model depending on your problem. This is the third part of my presentation. I'll talk about a little bit of robotics. I happen to coordinate a robotic working group at the AI lab of Stucky, and we are dealing with a robotic arm and also with Boston Dynamics Spot robot dog, this yellow one here. And mainly we're teaching them with reinforcement learning techniques in their virtual environment. So we have this Quasar Q-arm robotic arm as well. And what I did is that I I brought it to my daughter's kindergarten last October, and I showed them and explained them a lot, one after the other in 3 groups to the whole kindergarten that they could profit from this opportunity. And we were playing with a little robot dog. That's my daughter's. I showed them videos of the real Spot robot dog because that one I couldn't bring them. So you might see that projected on the wall. And they could also, so I made the robotic arm dance for them, and they could also touch it because I gave them an exercise, little exercise that they could do with my help. So this is a robotic arm. It's not so big. It's not an industrial robot. It's for studies demonstrate. And so the ratio of girls and boys in this kindergarten is like half-half, but let's confess it's very important. Well, maybe, I hope not only to me, for little girls already at this age, that we show them alternatives other than DOT and cooking. Because much later on, the ratio of girls in STEM science, it's very sadly low in this country. So I'm doing what I can, and I can promise I'll do that in the future as well. Actually, 2 days ago, I was demonstrating at Stucky to 12 and 14-year-old boys and girls as well. So yeah, the AI lab of Stucky is actually part and also the leader of this AI National Laboratory, MILAB, or let's call it MILAB 1. It's a 5-year project ending at the end of this year. And we are hoping so much that there's going to be a somewhat similar kind of MILAB 2 as well, knowing that it is so important. AI and applications are so important to the HANA network. So we are hoping the best. Anyway, the currently running MILAB has 6 work packages. And with our robotic tasks, we can basically touch more of these very easily. Machine perception, machine vision, no question. Then LLMs, large language models, visual language models, or sensors, detectors. And now let's go back to kindergarten. We will build block towers with reinforcement learning. Many of you might know what reinforcement learning is, but so for us, in our case, the agent is the robotic arm, and its environment is the tabletop with the colored blocks. It knows about the state, meaning, for example, with the locations of the blocks on the table. Then the teaching starts, the robot makes a move, an action, and our feedback to each action to motivate the robot is either a mathematical reward or a penalty, depending on whether this action is going toward solving the task or learning the task. And the aim is to develop a policy, a decision strategy, basically, which maximizes the long-term rewards. And like this, we make sure that basically the task we wanted will be learned. And now I will ask Gabor, because then I skip. Yeah, let's land on this one. And if we, yeah, this is genius. Thank you very much, because this is a PDF presentation, and Gabor told me that the video will go. So it can just go like this. Thank you. And so what if I tell you that this block tower building exercise is still too complicated? Would you believe me? Let's try whether we can break it down into smaller pieces. And in this case, we figured out that we can. So let's break then the block tower building exercise to smaller pieces, sub goals, which we call options. And in this case, that might be reach a block, grasp, lift, align, and stack it on another one. And from this point on, we have, thinking in these options, we have a planner, a high-level policy, which will choose the correct option depending on the state, basically either reach or grasp. And all these options, they have their own policies by the termination functions, reward functions, all these. For example, let's call a grasp on the blue block, and then this option will only deal with the fine motoric movement, the refer only to grab it. And yeah, this is what, one more time, please. Yeah, so then we solved this same hierarchical reinforcement learning way. This task, this children's task, it's not yet transferred all its knowledge into the real, into the head of our real robotic arm, but that also in the near future will happen. So somewhat more interesting feature than a robotic arm is this personal dynamics spot robot dog owned by Stucky. And well, you may say that's a quadruped, and ethologists prefer this naming convention, but I will still call it spot. And on top of that, it received the name Machkaku cat catcher in Stucky that still helps to spot robot dog. So it can do a whole bunch of things. It can shake hands, detect and follow someone, it can go on up on stairs, it can pull a chair or a human out of the ruins. But when competing with real dogs, it will still lose. So Spot as well, we are training with reinforcement learning. And yeah, a caveat. So these works with Spot and reinforcement learning, we only started this year. So please do not expect yet that to do some thought or whatsoever. But our simulation environment for Spot is NVIDIA's Isaac Lab and Isaac Sim. And I also apply to Hanan Cloud project we are currently running on the Saki branch. So we have in mind two kinds of exercises, two kinds of things for Spot. We definitely want to do professionally challenging tasks with Spot, with even room for publications. But it's also important to be able to demonstrate with such an expensive feature. So we are also working on some more or less spectacular demonstrable exercises as well. But now let's concentrate on the first one, the challenging tasks. So these weeks we are finishing up hopefully a safer integration, meaning that in the simulation environment of Spot, it will be integrated with a safety filter. Just think about the logic, which will then, for example, save it from going either too close or bumping into a moving object, which might be radiating or explosive. And we do this piece of work to a European Defense Fund project, the name of which I cannot even mention. Really. I won't. Another exercise, a longer term exercise, which we are already thinking about and started the preparations, is another one where we would like to use LLMs, large language models, visual language models, visual language actions, integrated them in our robotic tasks. For example, we can teach such a model on the video frames of the virtual robot dog when it is moving in interesting environments in the simulation. And like this in the future, we will be able to send the dog on the floor to look for someone and we will pass a vocal message. Or as commanded, Spot, please go back to the blue, I don't know, chair that it has already, or it has already seen on one of the frames before. Yeah, as I said, we don't have yet so much or Spot doing somersaults. We are these days actually we are extending and complicating Spot's repertoire, but at the moment, this is what I can show you some elementary simulation actions, because in the simulation it's actually quite normal that this robot Spot doesn't know anything. Even to walk or going from A to B, we have to teach it. And for example, thinking in the hierarchical reinforcement learning framework, going to a location could be one option, and stopping there without falling could be another one. Or we taught it to balance without falling off of a high plateau, which is a table for the moment. And as realistic physics is in action, so it can interact with its environment, for example, bump into things, into balls, and so on and so forth. And please then stay tuned for more with us on this. But with this, I'll like to then thank for your attention. Thank you for your attention.
Thank you very much, Vera. It was a nice overview from a very wide range of topics. Questions from the audience?
Ask a question about this energy project. You had, as you have told, you have taken into account a lot of effects that can modify the energy consumption. And is there any means to make it, to order it by relevance? So which are the most relevant effects, and how much relevant are they? So are they all relevant, or what happens if you just take into account half of them?
Yeah, so exactly this is the slide that I didn't put in because I thought it will be too much. So that belongs basically to the shapely additive explanations analysis, the feature importance basically, because you can, as this method, mathematical method, is indeed calculating for each and every feature the importance, basically the contribution in the final predicted value. You can visualize them, and there are Python tools to visualize them, I believe. So sorry that I didn't bring this slide, but you can then visualize which are the most important features. And then at some point, even you can cut, and without the rest, the results won't change. And you can also pay attention to, for example, the difference between our practice with the AI, even though we are not the most energetic electricity experts, in which it differs from Mavir's practice, that we directly use meteorological weather-related features in our model, and that already gave a lot to the interpretations and to the results, and that's why pretty nicely matched to the actual, whether it's the loss or the total load value. But yeah, you can visualize them. You can have a grasp on which features matter more. Yeah, but I mentioned, so the time-related and weather-related features, they matter really much. Yeah.
Further questions from the audience? Sophie, super.
Thank you for the nice talk. On average, or roughly, how long did the training take, or how much time did it take with the XGBoost model?
Well, it also depends on, it also depends how much data you have. And we were training on 3 years data, I think hourly resolution, with hourly resolution. And we were running these models on an 800 GPU, and I don't quite remember how much time it was.
Okay, thank
So
you.
eventually I didn't answer. Yeah, I don't I don't quite remember.
Okay. Any further things? Go ahead.
Thank you. So I have a question for this text to SQL or SQL project. So how well it actually generalizes? So can you switch the SDSS schema with another completely different SQL schema, or does it basically overfit on the SDSS schema, or how well it generalizes? That's the question.
Basically, that I also had to understand, and that's why I was discussing with our students. So the teaching in this case is completely different than for timelines, for example. Each and every question, we are training it with the our model, Vana AI, with the question code answer triplets, but each and every question is different from the other one. We downloaded so far the ones which are available in the SDSS Sky server. And so it will still learn, and you can still test with yet another question. And that's why we are using multiple metrics. And still the aim, and that is not so unrealistic, is that, so the key is that your database and its structure, the tables and the functions, those must be well arranged. And in many databases online, it's not the case. And the SDSS, I think Pista mentioned also yesterday, so these are very precisely, very nicely put together, huge databases, which astrophysicists are very precise people. And also this will be true in terms of the structure of the database for the Euclid project. And when this is sitting there, the database at this quality, then you could still use this model, for example. But in terms of training, it's so it's not many same kind of data, but different questions you are teaching it on.
Okay. Unfortunately, I have to cut the discussion, but we can still continue in the coffee break. I still have a couple of questions more, but let's move. Let's thanks Vera again.